Bryan in Ohio.
All right, thank you.
Oh, very good. We can see your screen.
All right, perfect. As we go through the talk, I'm just going to be sort of moving through issues associated with dealing with measuring light pollution. And I can give anyone more background about who I am at a later time, because what mostly I want to focus on is the fact that we're developing methods now because we live in a world at present where 80% of the human population, where they live, they cannot see the Milky Way. That means that there's 80% of humanity that can't look up at night anymore and be inspired to be the next generation of scientists and engineers and explorers, and where these people are cut off from cultural traditions that date back for a really long time and are separated from the ecological landscapes that natural night reveals. And probably interestingly enough, in the literature, we're also seeing that this disconnect for people in general, the resource of natural darkness and the natural cycling of light and dark is so engraved into our biology and our evolution that every single cell in our body has a circadian-based clock that ties us to these natural cycles. And that's what we're at risk of losing almost completely if we don't start thinking more broadly about this. And this would be visible light pollution from infrastructure. Artificial light at night is also what it's sometimes referred to, but overall it has a consequence, and the consequences are becoming more and more involved. This picture shows a lot of sky glow, but there's other types of light pollution as well. And what's important to remember is light pollution as a pollutant exists because of poor design. It's just a consequence of bad design, bad lighting design. And as a civil engineer, I'm probably have a different background than maybe everyone else on this call today. My awakening to this issue came in 2007 when I was in far west Texas. I looked up, I was there at night, I was camping out, I looked up and I saw a star-filled sky that I hadn't seen in a couple decades. And I thought to myself, well, why can't I see this? And the next second, I gave myself the answer because of civil engineering infrastructure. I figured it would be nice if I could better understand the problem and maybe do something about it within my lifetime. And that's what got me involved. So from a consequence of bad lighting, we have a lot of light that's out there that's completely unshielded. It's lighting the night sky. It's not really providing light where people need it or can benefit from it. And it goes from very bad to far better lighting designs that we have available to us today, which would be fully cut off fixtures, where all the light is shielded downwards at the right colors so that we don't continue to bounce light around the atmosphere once it's not being used. There's plenty of impacts for this result. And the more science that comes out, the more impacts that are revealed. And you can pick your favorite impact if I get you inspired enough to work on night sky related issues or become an advocate possibly for night skies, and pick your favorite topic and move forward with it. We waste about $3 billion a year in the United States providing light upwards into the atmosphere. And I got involved actually from a wilderness landscape preservation side. This picture was taken in Yellowstone, and the amount of light pollution that's starting to penetrate into our natural systems is concerning. This is a modern problem, and we see these are models showing the distribution of light over the decades. In the 1950s, light was mostly relegated to the large cities of New England and then Pacific coast. Through the 70s, light continued to spread across the United States to the late 90s and then almost till today. What we see is that light use per capita actually varies considerably by region, and even though that the amount of light coming out of a place like New York City is pretty high, the light use per capita is pretty low. It's in our western states that are still fairly dark where we have a lot more use per person than you would anticipate from the models. But we see this as growing. In the United States, we're growing our lighting footprint by about 1% per year over population growth. And it's not just a localized impact in the United States. It's actually a global phenomenon. Globally, we're seeing light growth by about 2% per year. And lighting at night is tied to human development in very strange and unique ways. It's certainly a marker of progress, and I'm not an advocate for not providing light for people, but I think we can do a better job with the design of it so that the light becomes a resource to use rather than a pollutant that takes away a resource. In terms of actually measuring light, we have a couple different options that are evolving. Options to look at sky quality, sky brightness, which would be looking up into the sky and seeing the impact of light domes, or how dark perhaps a certain portion of the sky is, or how light it is. And we also can look at upward radiance. So we can use measurements that go from above looking down to figure out what the footprint is. From a sky quality perspective, the Bortle Sky Index was actually developed and presented out in 2001 as a way for an observer, a citizen scientist, to begin to take data concerning the brightness of the night sky. And it's a visual index based upon established astronomical components where someone can look up once they're trained and tell you whether or not you're in an inner city type sky, a suburban sky, or in an excellent dark sky site. I like this graphic too because you can sort of see the impact of light pollution just in this one graphic that was well done by the International Dark Sky Association. The Bortle Index is a qualitative measure. It's somewhat quantitative in a sense that you can put a number to it, but it is subjective based upon an individual observer. If we're going to begin to remediate light pollution, then we need more quantifiable tools. And within the work going on now to measure light pollution, we're using both ground-based and atmospheric-based sampling systems in order to begin to develop out a fuller picture of the spread of light pollution and how maybe some of our mitigations or the new codes or lighting guidelines can actually be implemented and effective at reducing light pollution. And I'll just go through a couple of those. So from a remote sensing point of view, we have similar platforms to what have already been discussed today that we can pull information from satellites to CubeSats. Interesting to note, there hasn't been one mission dedicated to measuring atmospheric light at night yet. So it'd be, if anyone's interested in coupling some of the sensor platforms that are out there to specifically look at night skies or light upward radiance, then I'd be really interested in talking with you some more. We can put measuring devices on airplanes. We've worked with, and when I say we, it's really the broader community. People have been working with weather balloons in order to take some mid-range data. And I have a project right now with the University of Utah looking at developing a night sky drone to help take measurements from about 300 feet up. And then we can certainly take information from the ground. So what are we looking at when we begin to compile the available sources of data? The earliest measurements from satellites were done through the Department of Defense's Meteorological Satellite Program, most likely in the mid-50s, although the data from those satellites was held pretty close. The purpose of developing out these satellites was to inform weather patterns during military operations, but as one of the components was an optical line sensor, which gave us information about brightness on the surface as it was radiating upwards. The optical line scanners on the initial satellites gave a relative value for brightness, and at a resolution of about 1,000 of 1 kilometer. As time went on, there began wider spread interest at understanding light at night for different types of studies, one of which is looking at prevalence. And as time went on, the satellites actually evolved to gain not only relative brightness, but actually measure the amount of energy that's radiating upwards. This data is from the Tsunami National Partnership Orbiting Satellite and our National Polar Orbiting Satellite Partnership. This shows what's called the Visible Infrared Imaging Radiometer Suite. So it shows light in a day-night band. So this is the visual spectrum of upward radiance. And I pulled some data from upper Midwest. So you can see not only the footprint of St. Paul, so that the light that we use to light our cities, but also in the west of North Dakota, That's the Bakken Shale that shows up. The green area right below the shale is Theodore Roosevelt National Park, and I've done a lot of work with parks to understand sort of where they are in the the lighting footprint issue. And what we've seen, we can use the satellite data like VERS data in order to show what changes over time. So from 2012 to 2019, you can see this large explosion of natural gas production in the Bakken Shale. And if you were interested in protecting the lightscape of a national park, there's been a lot of light bleed, light trespass, and light dome that's grown around that shale development. So again, we're tied into lighting in various unique ways, and we can use measurements in order to begin to understand the impact of lighting on the night sky and on other resources. So VERS data, the scale was a little bit better. The resolution is 750 meters, so we get a little bit better data, but that's still not perhaps as good as we need in order to begin to understand the impacts. So to better understand the impacts, we can also take ground-based measurements. So one of the earliest measurement devices was just a single channel meter, sky quality meter, that looked at sky brightness in terms of zenith brightness. These have been widely deployed, some for longer term monitoring and also for a lot of citizen scientists and amateur astronomers trying to understand the quality of their night sky. We can do spectroradiometry on ground level. This system was developed by the National Park Service to do long-term baseline monitoring. I'll show you what some of their data looks like. But these are highly sensitive instruments that can really tell lighting on a pixel per pixel basis to look at long-term impacts on specific sites that we want to protect and monitor. At the same time, we can get right underneath lamps and actually look at the spectrophotometry. So what is that lamp putting out? What kind is it? And then photometry, how much light is that particular source giving us? And so these are all different ground-based measurements. And one of the keys right now is understanding how we can use ground-based measurements coupled to satellite measurements to better predict and to refine models. So from the National Park Service's platform, here's examples of the data that they're releasing. From the top left to the bottom right, progressively gets darker and darker. So the Golden Gate National Rec Area in San Francisco would show impact of the surrounding cities in California and the Great Smoky Mountains. You have the impact of Atlanta. Even though it's not right next door, you can still see the light dome from that distance. Chaco culture, you can begin to see the features in the sky providing the predominant light to the nighttime environment. But there are some cities that are far enough away to contribute to sort of the lightscape of the park. And then Death Valley, which is in some of the darkest lightscape that's left anywhere in the contiguous US. If we're looking under each fixture, this is a picture that I took when I was working in Yellowstone to help them manage their lightscapes at night. And we can use individual meters in order to go and figure out, okay, what type of source of light is this? What type of lamp there is? We're interested in color temperature when we're doing lighting design for dark skies, because anything with a really strong blue light footprint or blue light fingerprint or signature can refract around a lot. This is particular in the case for a place like Yellowstone, where about half the year you have snow coverage. And so we don't want to bounce light around if we don't have to. So we can use these spectrophotometers in order to talk about color temperature. In this case, the spectrum of this particular light, this is an LED. So when I was talking about the blue portion, this is a soft white LED, so that the blue footprint, it almost looks like a slug or a dinosaur in the spectrum. But in a bright white LED, that spectrum on the blue side would be larger than the rest of the visual wavelength. So what's interesting, like I said, is when we begin to combine data sources. So this is part of the data set from Yellowstone, where we have all these individual lights. So these lights are plotted according, they're all geolocated and characterized. And by knowing what's present, we can begin to use models or GPS models to actually overlay the lights on the ground with the satellite-based data and to continue to refine our models. So that's a little bit of background, sort of the multiple measures. I know I talked through things kind of quickly, but my goal is that we can, in the future, we can have better lighting designs to better manage our lighting so that the next generation of people can be better tied into the night sky than we currently are.
So thanks a lot, Brian. Let me start with a question, and that is, if you have a lighting installation, is it possible to retrofit it, or is this really mostly concerned with new lighting?
Yeah, absolutely. It's certainly, we're very much able to retrofit. And a lot of the work that I've done with the Park Service actually involves retrofitting existing fixtures. The good news is that lighting today is a commodity. And that's also the bad news, right? It's easy to get, the movement to LEDs is not necessarily a bad thing, but LEDs have really reduced the cost of lighting, the energy footprint or the fingerprint of the lighting, and actually our ability to provide lighting now in different places and at different times. So we can work with what's there, or oftentimes it's cheap enough just to replace lights that are no longer used for the purposes that they were intended.
And are there citizen science projects and stuff that are ongoing along these lines?
Yeah, there are. So one is called Globe at Night, and that Globe at Night project is looking to identify, they use the sky quality meter, or actually there are some of, we're actually able to use cell phone cameras in order to take some of the data. The challenge there is it's good data for trends, but maybe not the best data overall for quality. So the next generation is going to be requiring calibrated cameras to actually be able to do some of the work. And the quality assurance when you're doing citizen science is always sometimes challenging.
Are there other questions for Brian? Well, hearing none, thank you all again for attending this webinar. I will take this recording and break it into pieces and try to post them individually so that people could watch the individual presentations as they wish and get a hold of the individual presenters. Thank you again, and have a great afternoon, everybody.
Hey, thank you, James.
Bye-bye.
Thanks a lot, James.